That sounds good. Stuff.
Yeah, the stuff.
Acid base. Acid base, we'll finish that up. Then we'll get into the alkanes, cycloalkanes handout. Looks like we're ready to get started. Good morning, guys. Happy Friday. Quizzes will be returned during lab. As is stated on the syllabus, you need to put your course section on your quizzes and everything. Only about a third of you did that correctly. Either you left it blank or you put the wrong course section. I would reread the syllabus. That tells me you did not read the syllabus and take it seriously. Perhaps you missed other things in the syllabus as well. Please reread the syllabus. Okay, acid-base chemistry. Let's see where we left off at. Bases. Okay, a base is going to have a lone pair, and the lone pair is what's the business end of the base, right? Nothing new. The more electron rich the lone pair is, the more electron density there, the stronger the base. How can we make there be more electron density there? We can donate electrons towards it. Maybe inductively, maybe by resonance. If you pull electrons away from the lone pair area, that's decreasing the electron density at the lone pair area. That makes it a worse base. We actually looked at base strength when we looked at acid strength. When we looked at the conjugate base, we looked at the stability of the conjugate base. More stable the conjugate base, the more willing it was to just exist as is. Less stable, the more it wanted to go back, take the H and go back. Those are the same considerations. We were doing some examples below. Let's see how we did on these. Which is more basic? Did we do this one in class? Yes. This one more basic, yeah? Lone pair is sp3, the other lone pair is sp2. sp3 lone pair is more out there. sp2 lone pair held tighter to mama. Not going to be able to react with protons as well. That effectively reduces the electron density by pulling the electrons closer to the nucleus. Which is more basic? This guy or this guy? This lone pair is in what type of orbital? sp3. This lone pair is in what type of orbital? P. Here's a take-home. Lone pairs that are in p orbitals are not basic. They're busy doing resonance. They're busy conjugating. This lone pair is conjugating with the neighboring p orbitals. Put that in the p orbital, right? Boom, it's now conjugating. And what it doing that is not basic. Now there will be an exception or two to that. There's an exception to everything. But there's your statement. Lone pair in the p orbital, not basic. It's busy doing something else. This lone pair is sp3, it's basic. And sp3 nitrogen is a pretty decent base. Even though it's neutral. Your strongest bases are anions, negative. Your negatives really want to get taken H+. And sp3 nitrogen is a pretty decent base. sp3 nitrogen is a pretty decent base. And sp2 nitrogen lone pair is mildly basic, not as basic, less basic, right? We'll clarify what is a good base. So this guy. Which is more basic, F- or Cl-?
Oh, that's nice.
F-, why? Because it's what?
Less stable.
No, if it was less stable, it would be more basic. Because if it's less stable, that means it don't like being like it is. It wants to go back to neutral. I'm sorry.
We look at it opposite the way we did
No,
acid.
no, hold on. What I just said was asbestos.
Okay.
Okay. Let's start over. Tell me again. F minus is, okay. All right. I heard you in my mind say it was less basic, and I was trying to explain, and then it all just was backwards. It's less stable. Yes. That's why it's more basic. CO minus is more stable. Why is CO minus more stable? Because it's bigger. We talked about that. We're using the same arguments, but we know how to apply them. Yes, it's more stable. F minus don't want to be minus as much. It would love more to find a proton to react and go back to neutral HF. Okay? Right? When this acts as an acid, what does it become? Well, I'm sorry, as a base, what does it become? This is backwards thing. Okay, when it acts as a base, that means it reacts with H+. What does it become? It becomes HF, right? And our mechanism is the lone pair reacts with the H. You can draw it as generic H+, but this is really connected to something like HCl or something. It goes back here. Now the F is happier because it didn't like being minus as much. F minus is a stronger base. Which is a stronger base, ammonia or water? Coming out of Gen Chem, you all know ammonia, but I don't think you really understand why. Why is ammonia a good base? It's got to be more than because it was on some list somewhere. Why is ammonia a good base compared to water?
Isn't it because the nitrogen is less electronegative?
Yes, nitrogen's less electronegative. So what does that then lead to? You've got a lone pair. Think about oxygen. What does oxygen do with the lone pair?
It wants to keep it.
Inherently pulls it tighter. The electronegativity comes from the nucleus, really. The nucleus pulls it tighter. Why? Because there's more protons in the nucleus of the oxygen. That's what electronegativity is all based on, right? Yeah. Oxygen's a better parent. It's not a hybridization effect. They're both sp3. That's not your argument. It's electronegativity. Oxygen just inherently holds them closer, even though the hybridization is the same. Nitrogen's not as good of a parent, okay? Unless it's lone pair get out there and, do acid-base stuff. Oxygen won't let the kids out of the house. Oxygen's a better parent. Nitrogen's a worse parent. Yes. Ammonia, better base. Which is a better base? 2 carbanions here. They're both pretty strong bases, but which one is stronger? Well, what's the difference? This has extra sp3 carbons. What do?
Donate.
They donate. Okay, so which one has most electron density at the business end? This guy, because it has extra donation, because we know the effect of an sp3 carbon or carbon chain, right? And so the electron density is like this, but over here it's more like that, because you got some pumping in here. Because these electrons in these bonds aren't just fixed statically, they can be polarized, right? That's dipole. Right? They can be polarized. They don't have to be fixed, but they can be more like this. And carbon likes to push. You're an sp3 carbon, what do? Yeah, you actually push. That's just a statement we've made. We can talk more about why, but it's really kind of more advanced. It's called hyperconjugation. Okay. There's some prediction of bases in some of the, or all of the main trends and things, types of arguments you make. DQ page. Or actually quiz page. Haven't got your quizzes back yet. Some of you have not. Levitra. What's the most basic atom in Levitra? Where's the base? Take a look for it. You want to look for the most basic. That's the one. What's the most basic atom in Levitra? This oxygen? First off, base has a lone pair, right? Bronsted-Lowry, lone pair. If this reacted with an acid, which atom is going to react? This oxygen? This sulfur? This nitrogen? What do we want to hone in on? That's the type of question we may want to be able to answer. And what we just did at the bottom of the other page is the starting point, and really, the information you use to answer such questions. Okay, we mentioned it on the previous page, but a neutral nitrogen tends to be a good base. Of your common atoms, much more basic than a neutral oxygen because oxygen is a much better parent. In nature, you find a lot of compounds that have basic nitrogens in them, neutral. Okay? And I can look at this compound here instead of Levitra. Okay? This is a page of what's called alkaloids. What does alkaloid mean? Alkaline-oid, humanoid, human-like, alkaloid, alkaline-like, basic-like. These have basic-like properties. Why? Because they all have a basic nitrogen in them. And a lot of your natural products a class of them is called alkaloids, ones that are basic. A lot of these have maybe some interesting psychedelic properties, like LSD. Alkaloid. Okay. A number of them are listed. Have y'all mentioned alkaloids in like biology class? Okay, an example, ergoline. Which nitrogen is most basic? Again? On the top, why? Yes, correct. Top one. Because the lone pair is in what type of orbital? sp3. This lone pair is in what type of orbital? P. What do we know about lone pairs of p orbitals?
They're not bases.
Okay, there you go. Any other atom more basic than nitrogen? Well, obviously not, because no other atom even has a lone pair. What if there was an oxygen? Would you think the oxygen was most basic? No, oxygen's a better parent. Oxygen holds lone pair tight. A neutral oxygen is never typically basic. Once you make the oxygen minus, like hydroxide, now it's basic. But a neutral oxygen, not basic. Neutral nitrogen? Yes. And here's a list of a lot of interesting molecules. They contain basic nitrogens. Morphine. So that's an important class of natural products. Equilibrium. You know how to use pKa's to judge equilibrium. Reaction will favor the side with the weakest acid. But you did this over and over and over and too many times in Gen Chem, right? You know all this. All right? For example, we take this, it's the same reaction we showed on the previous page. We take this here with water. I'm giving you a pK of water of 16. We can do a reaction, okay? Okay, that's 2 molecules, but pretend it's 1. What's the most basic atom in the circle? Because in any acid base, you want to identify the base and then the acid. Let's identify the base first. What's the strongest base in the circle? The what?
The carbon.
Particularly atom. What's the most basic atom in the circle? A neutral oxygen or a negative carbon? Yeah, carbon don't like being negative because it's not that electronegative. Right? F likes being negative more. Okay? There's your strongest base. What's your strongest acid in the circle? An H on a carbon or H on oxygen? Well, we talked about that, right? You'd rather have a minus on oxygen, so it's going to be more served as the acid. So that looks like the base, that looks like the acid. Okay? Now you got your acid-base mechanism, right? You got water. These electrons take the H, these move over there. It's the same mechanism. It works 100% of the time. Only one mechanism. It's got 2 arrows. I highly recommend you understand that mechanism if you want to understand acid-base chemistry. What does this outcome give? Well, it gives that on the right. That is, the carbon is now bonded to another H. Well, we can draw that. It's condensed. And then I'm not showing out all the bonds. And then what does this arrow mean? Right? The lone pair moves over to the oxygen to become what? It's all there in your arrow movement. So, every equilibrium has got an acid and a base on each side. It's called the base, that's called the acid. The base becomes the conjugate acid, and the acid becomes the conjugate base. That is, the acid on this side is called an acid, but on this side it's called a base. That's a base, but on this side it's called an acid. Well, the acid over here is 16. The acid over here is 40. I'm giving you that. Based on the pKa's, which side is favored?
The right.
The side with the weaker acid. Which side has the weaker acid? Well, 40 is the weaker acid, right? This side's favored. Favored by how much? Favored by the difference in your pKa log, which is what? 10 to the 24. Right? Difference is 10 to the 24. So it's all the same thing you did in Gen Chem. Y'all do a lot of equilibrium in Gen Chem? Okay. It's all there, right? Let's look down here. If you take this compound with water, do an acid-base reaction, okay? What's the acid? What's the most acidic H in the circle? I've kind of already given this away because I listed the pKa under the acid. But if you say what's the most basic hydrogen in the circle, it's going to be this one right here. Why is that more acidic than the H's over here? Yes, resonance, right? pK of 5. Water has pK of 16. It's less basic. This is your acid up here. That means water here acts as a what?
Base.
Yeah, water here acts as a base. So these electrons take the H. I would always recommend drawing in your bond. Okay? Drawing in your bond so you can take the H and then these electrons can move here. What does that give? It gives this minus, right? That's what that arrow gives. When water is bonded to another H, it's actually H3O+. Again, that's condensed. You can draw it all out. Here's your reaction. The acid over here is this. It's about 5. What's the acid over here? Yeah, how do I know that's the acid over here? Because that's where the H is now. If the H was in red, that would be red, and that H would be where? Now it would be one of those. That's the acid over here. That's 5. That's actually hydronium. pK is less than 0. Which side's favored? 5 or less than 0? The weaker acid's favored. This side's favored. By how much? Well, if that's 0, it's 10 to the 5, or even more, depending on what that actually is over there. Okay? So question here. When you put, this is acetic acid, when you put acetic acid in water, does it completely ionize? No, the favorite is for it to exist here. In fact, out of every 100,000 molecules, 100,000 exist like this, and only one is ionized. It's 1,000 to 1. I mean, 100,000 to 1. 100,000 to 1. So that reaction is actually not favored. Okay, let's try the ones below. Show the result of this acid-base reaction and tell which side is favored at equilibrium. We're going to do all these. Now, I've already given you kind of some hints. Maybe other problems there will be less hints. This is also a molecule we saw on the previous page. Right? Can you see my lone pairs? How we do? How we do, everybody? Questions?
For a test, would we need to draw on the lone pairs on the water?
Here's where I would really want you to draw lone pairs. If there's a charge, I would want to show lone pairs because it's just you got something going on here, and otherwise it's just kind of typical. Okay, that's water. Okay, the lone pairs are there. But here, I would really want you to clarify. Hey, there's 2 lone pairs here. That's why it's a negative charge. You know, if you didn't show lone pairs over here, I'd probably let you slide, unless the question said, like complete full Lewis structures, etc. You know, sort of just the way I did it. I intuitively made sure I had lone pairs on that anion, but then water, I kind of just wasn't as critical. How'd we do? Everybody use your acid-base mechanism? I didn't show it, but I did in my head. What? These electrons do what? Take the H, these electrons move here. How many electrons on the nitrogen to begin with? 1 lone pair. How do you get a second lone pair? Well, it's right here, right? Okay. Which side's favored? I gave you this. It's about 8. What's the acid over here?
16.
Water is 16. Which side's favored? Weaker acid, which is water. So this side's favored by how much? Yeah, what's that? 100 million? Well, 10 to the 9 is a billion. 100 million. At equilibrium, you got 100 million of these, and only one of these left. That's pretty much complete, right? If you did a percentage, that's like 99.99999%. Is hydroxide strong enough to deprotonate cinnamide? When we remove a proton, it's called a deprotonate, right? Is hydroxide strong enough to do that? You get the question? Is hydroxide strong enough to do that? Why is it? Why are you saying yes? Do what? Okay, I'll assume you all understand that. Next one. Next one. And there's two more below that. This one's going to be anybody know the name of these NO2 groups? They're not on your functional group, but you do cover them in organic 2. Yes, nitro, N-I-T-R-O, nitro, like nitroglycerin. Nitroglycerin has 3 nitro groups. Yes, nitro is a common, it's a functional group, it's a nitro group. But it wasn't on our list, you'll see it in organic 2. That'll be the anion, right, plus what? What do you got over here? Plus what? Ages on the logo. Not fully correct. Not fully correct. Not fully correct. Looks good. Looks good. Yeah, nitrogen has, what are those? Ethyl groups? Ethyl groups, and what else? Now an H, but that's now a positive charge, right? If you don't have the right charge, it's not correct. Positive charge. Because we know in every acid-base, right, every acid, conjugate base, one's neutral and one's charged, right? If that's neutral, then that's charged. If that's charged, then that's neutral, right? Y'all picked up on that in previous classes? By the way, that's just a little pointer. On the back page, there's a list of kind of free information. And probably one of the entries there is pointing out the fact that one's neutral, one's charged, right? So you got to have charges. That's not a typical nitrogen in it, is it? That's not 3 bonds, 1 lone pair. So it's probably going to be charged. Okay, which side's favored?
I don't know because we only knew the pKa of water. We don't know these.
Yeah, well, yeah, you actually know both. So let me explain why. What's the acid over here? What had the H over here? First off, did we do it right? Is that the most acidic H in the circle?
Yes.
Well, that's nothing but CHs. CHs aren't acidic typically. All this is CHs. I mean, where would you rather make a minus on that oxygen? It's more electronegative. It can handle the minus better. It's also very resonance stabilized. It's got resonance. The new lone pair, if you want to consider the third one the new one of them is in a p orbital, right? It's very stabilized by resonance. Okay. Is this a decent base? It's a neutral sp3 nitrogen, like an alkaloid, right? It's a good base. The good old acid-base mechanism. Draw your bond in there so you can have a bond to work with. These electrons here, and then these electrons move here. That's how you get that outcome. This is the acid, it's pK of 1. What's the acid over here? That is, what has the proton over here? This guy has the proton now. You see it here in neon red? What's its pKa?
10.
Its pKa is 10. Yes. It was given right here. Because this is a base. Why am I giving a pKa? Because in organic chemistry, and I think in most chemistry, we actually use pKa's for bases. I've never used a pKb in my life, other than when I took Chem. From then on, you use pKa's. But if you give a pKa for a base, it's actually referring to what? Yes, it actually refers to the conjugate acid. Because otherwise it's useless, because this describes an acid equilibrium. But this is not acting as an acid. But over here it is, because if you go that way, this acts as an acid if you go that way. Because if you go that way, these electrons take this H and these move here. And that arrow movement gives what? It gives back the other side, right? Okay, there's others to do down here. I want to let you do them on your own so we can move ahead and you can take some time and do those. 2 different molecules. When I say comment on this, I should have said that up there. The comment is there. Comment on that. It's the same thing down here to consider. Here's another example. That's NH2, yeah. It's the same thing, except the acid and the base are just connected in the same molecule. That makes it no different, though. For example, back up here, I mean, that could have been just one molecule connected. We still identified the strongest acid and the strongest base. It doesn't have to be 2 separate molecules. So please give those a try, and we'll look at them on Monday. You not doing?
You gonna be here Monday? I'm not.
I'll be here. You want to be here?
No.
Okay.
Not on Labor Day.
You'll be laboring? Okay, let's see what's on the next page. Function applications. What about pH? What about pH? Henderson Hasselbalch equation. I'm not sure if you've seen this before. You'll certainly see it going forward more in biochemistry. Okay, Henderson Hasselbalch. It brings in pH. Okay, it's an equation. In biochemistry, you used to derive this. Okay, lots of paper, and end up with this equation. It says that pH equals pKa plus the log of the B over the A. This is just basically your acid conjugate base pair. The B is the basic species, and the A is the acidic species. There's a log of this ratio in terms of concentration. We'll do this. Take home though, basically it's 3 variables. And if you know 2 of them, you can solve for the other. And most commonly, for example, maybe you know these 2. If you know these 2, then you can solve for this ratio. And you can tell the ratio of your acid to base pair. Okay? Let's see how this works. You can read this. I'll get straight to the take-home. In summary, if pH is greater than pKa, B will predominate. It just comes from working the numbers. You can sit down and think. Because if pH is greater than pKa, pH is greater. That means like if this is 8 and that's 7. Right? That's greater than that. So for this to work, this has to equal 1 in this simple. This has to equal 1. So 7 plus 1 is 8. For this to equal 1, B has to be greater than 8. That's where it comes from. B will predominate. On the other hand, if it's reversed, A would have to be the larger number. So if pH is less than pKa, A will predominate. There's your take home. Let's try to use this. Acetic acid. How will it exist at pH of 7, which is blood pH? That is, will it be in the, we're talking about conjugate acid-base pairs. Will it be in the acidic form or the basic form? Well, what is the equilibrium? This is an acid, so it acts as an acid and becomes, it gives up a proton, it becomes this. This is the conjugate base. You have to be able to show that. The acidic species is the one that contains the H. This is the basic species. It does not contain the H. So there it is. Which one predominates at pH of 7? What do we need to know? We need to know the other variable a little bit. Okay. The pKa of this is about 5. So, which is going to predominate, A or B? Well, you can read, but let's look at it as if the answer is not there. Let's see. pH is greater than pKa. Importantly, a lot of times you guys get this backwards. pH is a thing that can vary. This is a constant. That's not going to vary. So what you're saying is, the thing that can vary, right? Is it on the high side or the low side? Okay, that's a constant. That thing can vary. Is that on the high side or the low side of the constant? 7 is on the high side of 5. The high side, is that the basic side or the acidic side? In terms of like pH. High pH is basic, right? Yeah. This is on the high side of the constant, which is the basic side. The basic form will predominate. By how much? By the difference in your log units. By 2, 10 to the 2. Okay? B will predominate by 10 to the 2. That means at equilibrium, you'll have 10 to the 2 of this and only 1 of this. So what's that? 10 to the 2 is what? 100? So it's a 100 to 1 ratio. That's how you use this. Okay. Well, there I'm just telling you that one would be an ion, one would be neutral, right? But you already know that. I just pointed that out. Ion neutral, ion neutral. Acid-base chemistry. Well, that's what we're doing, right? Codeine. Most drugs are given as salts. This was mentioned in the solubility lab, right? Why? Because it makes them more soluble in water. Okay. Not soluble in water, that is ionic charged, more soluble in water. Okay. What type of properties does this compound have? We've got this nice basic nitrogen. Okay. We can react it with an acid, like ACl, and we can get this outcome here. Is this reaction going to be favored, though? Well, we need to know the pKa's. pK of the acid, ACl, is about -5. What's the acid here? This guy. It has a pKa of about 10. Which side's favored, -5 or 10? 10, the weaker acid. So yes, this is favored. By how much? 10 to the 15. That's what? 100 gazillion. This is strongly favored. Now, hopefully you would intuitively know that because we're reacting it with a strong acid. It's going to just move towards the products. Okay? Okay, there's questions there. Basically, you need to start looking for types of questions and applying this information. On the back is free information. Okay? Miscellaneous points to remember, kind of a summary. No extra charge for this information. Okay?
Because we're on the same.
We have warm-up questions, have daily questions. Before we move to the next handout, which is our last handout before the test, you know, when we come back on Wednesday, we'll have 1 week before test. So don't let this weekend get away from you. Alkanes, that's our next and final handout before the test. It is a good bit, particularly we'll be getting into confirmations. Please be doing some reading about confirmation because on Wednesday we will be hitting it hard. Any questions up to now? Acid-base chemistry. Using your acid-base mechanism to predict any Bronsted-Lowry acid-base reaction. Being able to use pKa's to assess equilibriums, which sides favor, Henderson Hasselbalch, bringing in pH. Identifying strongest bases, strongest acids. But if you're going to do an acid-base reaction, that's what you want to identify, the strongest acid and the strongest base. Because the strong base ain't going to go over here and react with the weak acid. It's going to react with the strong acid. Questions about any of that before we move ahead? DQ questions? Okay, let's move ahead then. You guys are eager to move ahead. Alkanes, cycloalkanes. Nomenclature. I had a dream the other night. I asked for questions and like, everybody raise their hand. I got a question.
Nightmare.
I'm like, okay, let's talk about them all.
Well, I had a nightmare that I didn't know anything about.
Didn't turn out that way. Didn't turn out that way. So all I can do is plow ahead, right? All right, well, let's plow ahead. Nomenclature of alkanes. This is by video. Any questions about this? Any questions about nomenclature? We have the right. Whatever all this, got your prefixes, yeah. Meth, F, prop, but, int, X. Stop sign. Next time you see a stop sign, recognize that it's an octagon, right? Octane. Question. Oh, she had a question.
Yeah, she.
Oh, if you know, like, when you're saying, like, there's, like, the common names for, like, certain groups.
Isopropyl, isobutyl.
But, like, in how you did it, like, one of them had, like, an acronym, but she didn't use it, so, like,
Well, it's a common name. IUPAC doesn't really use common names.
okay.
I mean, it's standardized IUPAC is not a common name. You can use common names sometimes. On questions, I may say IUPAC only, or I may say you can use common names if you want. As an organic student, I would recommend you be familiar with common names. Question?
Sorry, that was just a she.
Question over here. No? Okay. Thinking the video, I did not work this one here. Is that right? Is that right? Yeah? Okay, let's do this one. I assume I did the rest. Longest continuous chain here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's actually right through here. It turns out it just happens to be right through there. It is 10, right? Everybody's already done this one, right? 10. So what do we have? A decane? Decane is circle. What's on the decane? What is here?
Propyl.
Yes, we got a propyl. It's just a straight chain propyl. There's nothing complex about that. What's the other thing?
Good ethyl.
Has a methyl.
It's also a propyl.
Purple.
Because it's 1, 2, 3. Coming off the parent, we got one, the longest chain of the substituent is 3, right?
One methyl purple.
So that's a propyl, 1, 2, 3. But what's on that propyl? You see, that's not just a straight, simple sub. It's a sub that has a sub of its own. And we call that complex. So there's a propyl, but it has a sub of its own. What's the sub on that? Methyl. And what position is the methyl? 1, because the 1 position is the first carbon coming off the parent. So that's actually a 1-methyl propyl, and that's called a complex sub. But that starts with M and it starts with P, and when we list them, we'll list it in alphabetical order. But, so this has 2 subs. What's the numbering on the parent? We want to get these subs the lowest possible numbers. 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. It's 5, 6 either way you go. So how can we break that tie? Or how do we want to decide then if you got 5, 6 both ways?
The complex.
It would just be in alphabetical order. Yes. So M comes before P, so this would be 5, 6. So that means that's 1 and that's 2, 5, 6. We list these out like that. And at the 5 position, we have a what? A 1-methyl propyl, and all that's in parentheses like that. Don't forget your dashes. Usually dashes after numbers. And after things like this. And then, that's 1 substitution. At the 5 position, we have that. And then at the 6 position, we have what? Plain propyl. That's just one word. There's no dash or anything. It just flows there. There's your name. Did we get it right? Question?
So this one, if you said IUPAC, that's IUPAC, but if you said common name, could you use sec-butyl?
Okay, good, because this does have a common name. Yes, that is a sec-butyl. Butyl, I thought it was a propyl. It was because with the common name, it's the total number of carbons. It's 4 total, so it's some type of butyl, but it's not a straight chain butyl.
So would it be,
The sec comes from that being a secondary carbon. Well, see, this is a little bit misleading. It's actually tertiary because of this one. But if you forget about this one, then that's secondary. Okay? I don't like it because formally it's tertiary because we include that one. That's where the sec-butyl. If you just look at it without anything here and ignore that, then you say that's secondary because it's connected to 2 carbons. Depends on if that's another carbon or not if it changes to tertiary. Yes. So you could say sec-butyl. Sec-butyl, the B would be the alphabet, and you could just replace that with sec-butyl.
okay.
So in parentheses, you would just have sec-butyl. And it would require no numbering or anything.
Oh, so you wouldn't have 5?
No, I'm referring to this one.
Oh, okay.
It would be 5 sec-butyl.
Would it still have to be in parentheses even though it didn't include a number? Or does it matter?
I would because you got that dash in the sec-butyl, and I think it should be in parentheses. I don't know if that's the official answer, but I would put it in parentheses. Now you can get the nomenclature book in the library. It's about this thick. Okay. We're really only going to be doing page 1 of that throughout the course. Okay. The other 999 pages are for more advanced stuff. It used to be blue, and we call it the blue book, blue nomenclature book. Imagine naming some of those alkaloids. Instead of naming it codeine, how about an official chemical name? It can get quite complicated. Okay. Cycloalkanes, with any questions here? I covered all the front. Alkyl halides, did I do these three in the video? I don't think I did that one. Did I do this one in the video?
No.
I don't think I did. Let's do that one. Longest continuous chain. 1, 2, 3, 1, 2, 3, 4, 5. 5. Either way you go, it's 5 here. Or I could have that be included. 5, right? What's that, pentane? What's on the pentane? Have an iodo, chloro. These are just named like bromo, fluoro. What else is on the pentane? A methyl. Because that one is included in the parent, but this one was not. What's the 1 in?
Yeah, I am.
Well, again, it's like a choice. If this was 1, we'd have 2, 3, 4. If this was 1, we'd have 2, 3, 4, right? So we have to do alphabetical. I before M. I don't know, instead of putting the methyl, if we do that, call this 2, 3, 4. Is it 2 iodo? Actually, when we list it out, we probably want to list the chloro first, right? 3 chloro.
Oh, I see.
2 iodo. That doesn't have to be capitalized. 4 methyl. That's just one word. Is that right? Does that look right?
Would it matter if you had chosen the parent chain to be the linear?
No, it would have been the same exact name.
Okay.
I mean, if we'd done that, it'd be 2, 3, 4, and you got a methyl at the 4. It's the same exact name.
So sometimes you see compounds labeled with a comma in between numbers, so 1,6 fructobisphosphate or whatever.
Yeah.
What is
If
that?
we had another methyl here, it still would have been a pentane. But for the methyls, we could have said 3, 4 dimethyl.
Okay.
Because you don't have to, if you got 2 methyls, you don't have to keep them separate. For example, if you had 3, you could say trimethyl. But you do need to indicate where all 3 are at. So you do have to have 3 numbers. In some cases, they could all be on the same position, and so it might be 4, 4, 4 trimethyl, although I don't think that's possible. Please have a safe weekend, guys. See some of you in lab this afternoon.